There are many things in the world that are each other's opposites. Hot and cold, for example, light and heavy, wet and dry, fiction and non-fiction. But there are also some things that have opposites that you would not really expect to have one. One such a thing is matter, the collective word for the stuff that stuff is made out of. In some sense, its opposite is antimatter. You might have heard about it in science fiction, and although sci-fi has a questionable track record when it comes to talking about stuff that actually exists, antimatter is absolutely real. Studying it even gives us a tremendous insight into the inner workings of the universe, to the extent that it might lead us to an answer to one of the ultimate questions. Why is there something instead of nothing? No joke, antimatter is one of those things that sounds fake, but is very real and very awesome. So, today, on Fundamentally Explained, what is antimatter and why is it so friggin' awesome? In some sense, antimatter can be seen as the opposite of ordinary matter. What does that mean? Well, let's look at a specific ordinary matter particle, the electron. The electron is such a normal matter particle, so it has an antimatter equivalent. This antiparticle is, very creatively, called the anti-electron, or, a bit more creatively, the positron. The electron is not unique in having an antimatter partner. Also the muon, for example, has an antimatter equivalent, called the antimuon. The up has the anti-up, the charm has the anti-charm, and so on and so on. But for simplicity, we'll ignore all that for now and zoom in on only the electron and its positron partner. The electron and the positron are actually incredibly alike. They have the same mass and are both charged. They differ, however, in that some of their properties have a flipped sign. The electron is negatively charged, for example, while the positron has a positive charge, hence the name positron. The charge has the same size, it's just that the minus sign in the electron is now a plus sign in the positron. To get a sense of why this is, not an explanation, just a feeling, you essentially only need to know one thing. Charge, like the electric charge of the electron and the positron, is a so-called conserved quantity. This means that no matter what you do to particles, whichever particles, and no matter how many interactions you subject these particles to, the total charge of all particles combined is constant. You cannot change or create new net charge. It's just impossible. Can't do it. And this has a couple of interesting effects. In an earlier video, link in the corner and in the description below, we saw that we can describe particle interactions with Feynman diagrams. In a Feynman diagram, particles travel along the lines in a diagram. You can connect lines in vertices, representing the interaction of two or more particles. For instance, the process of an electron emitting two photons, two light particles, can be clicked together in a diagram like this one. Back to conserved charges. Let's look at this diagram, in which we start out with two electrons. Electrons are negatively charged, so the initial charge is -2. If total charge is conserved, which it is, and the initial charge is -2, which it also is, then this should be true everywhere in the diagram. It's clearly true in the beginning, and it's also clearly true at the end, where we again have two electrons. But it's not true in the middle. The photon is not charged at all. This means that in both interaction vertices, some charge is lost or added, and therefore this process simply cannot happen. Yeah, okay, you can draw its diagram, but that does not mean that it can happen in real life. You can draw anything you want. What can happen though is the interaction in which one of the electrons is swapped with its antiparticle. As we saw before, the positron is positively charged. So with this change, the total charge at the beginning of the diagram is -1 plus 1 is 0. And if we also change this in the right part of the diagram, suddenly things work again. The total charge is 0 everywhere in the diagram. Here, an electron and a positron hit each other, briefly change into a photon, and then change back again. This tells us that, apart from a changed sign in the charge, the charges of the electron and positron indeed must have the same size. If this weren't the case, they would not add up to zero, and the photon would have a residual charge, which it hasn't. Antimatter is thus the same as normal matter apart from some properties that flip sign. Properties like the electric charge. Not that this is the only such property, but it is the most well-known one. Now, because physics remains unchanged by the antimatter flip, antimatter particles are, just like normal matter, able to come together to form atoms. Anti-atoms, to be more precise. This means that they can also form anti-molecules, and in theory they could even form anti-objects, an anti-Bob, or even an anti-universe. But wait, if antimatter is that simple, why all the hype and this entire video about it, if it is as basic as flipping a sign? Does it even matter? Well, no, quite the opposite. Please keep paying attention, it anti-matters. No, but seriously, it does matter. Because this simple sign flipping thing results in some truly counterintuitive physics, which you might have already noticed in the process we looked at. We started out with two particles, each with a charge and a mass. But when they touched each other, they changed into another particle, the photon. A photon is light, both in the sense that it is a particle that forms light, and in terms of weight. It has no mass at all. Mass disappeared and changed into energy. And to make things even weirder, at the end of the process, the opposite happened. There, the no-mass photon changed into particles with mass. Welcome to particle physics, where the concepts of mass and energy get increasingly weirder as you dive deeper. Please have this customary t-shirt. Now, not all interactions, and therefore not all exchanges between mass and energy, are allowed. There are rules governing this, including the conservation of charge we already saw before. Luckily, most of these rules are automatically adhered to when considering interactions between particles and their antipartners. For example, interactions in which a particle and antiparticle pair destroys each other, or diagrams in which these pairs are created, generally don't violate any of these rules. These processes are so important that they have been given their own names: annihilation and creation. Note that it is impossible to create or destroy only matter or only antimatter in these interactions. Conservation of charge remains a thing, so you will always destroy and create matter and antimatter in equal amounts. Always? Always. Always, always? Yeah, well, no, yeah, but wait a sec. We'll come back to that. For now, let's just say that, yes, matter and antimatter are always created and destroyed in equal amounts in particle interactions. To make sure that we don't make mistakes in our diagrams that would violate this rule, the standard technique is to give matter particles arrows that point along the travel direction of the particle, while at the same time giving antimatter particles arrows that point in the opposite direction. This should always result in a flow when following the arrows in a diagram. A flow that we didn't have in our original 2-electron example. The reason sci-fi is interested in antimatter, to link back to the beginning of the video, comes mainly from the possibility of annihilation that antimatter allows for, namely because its result is pure energy. For example, through a diagram like this one. In other words, you could use antimatter as an extremely efficient and clean energy source. Just have two things touch each other. No residual products, no CO2, no nothing, just energy. Sounds ideal, so you might be wondering why we're not doing this. And I'll be honest, there's not a single reason for this. Sorry, let me say that again. There's not a single reason for this, but multiple. The biggest of them might just be this one. Where do you get antimatter from? You can't exactly buy it on Amazon. We can try to create it with particle interactions, yeah, but how do you make these interactions happen in the first place? By putting energy into it. A lot of energy. At least as much energy as the annihilation process produces. So when creating antimatter ourselves, it's not giving us a net energy gain. But do we really have to produce it ourselves? If matter and antimatter are always produced in equal quantities, and everything around us is made out of matter, shouldn't there be an equal amount of antimatter somewhere? Yeah, so where is it? Is it somewhere at CERN? Is it at the center of the Earth? Is it in the hands of the US government, who keeps it safely guarded in Area 51 in a secret basement beneath the secret basement where they keep the aliens and the real Declaration of Independence, you know, the one with the secret map on the back? Well, no. As said, you can't let anything touch antimatter, so hiding a universe amount of antimatter inside something made out of normal matter would be challenging, to say the least. It is, however, a good question, for the following reason. If matter and antimatter always create and destroy each other in equal amounts, but there are no significant amounts of antimatter around, why is there still ordinary matter? In other words, why is there still something instead of nothing? A good question without a good answer. I mean, yeah, there could have been a purple titan who was very inevitable and also snapped away exactly the antimatter half of the universe. But what are the odds of that? How truly inevitable is such a scenario? Luckily, science has some better, or rather more plausible, ideas of how to solve this puzzle, but the full evidence for these ideas is still to be found. The most common idea is this one. Imagine you have a neutral particle, that's to say, a particle without electric charge. Without violating charge conservation, you could change this particle into its antiparticle. But physics is the same for antimatter, so the opposite would then also be possible, of course. On a large scale, the balance between matter and antimatter would remain the same because of all of this. But what? What if there were some quirky physics that would allow for different rates for these processes? That would create a mechanism to change the balance of the matter-antimatter scale. This may sound a little far-fetched, but we already know of the existence of such processes. Unfortunately, the collective effect of these processes is not large enough to explain why we currently have as much matter as we do, but hey, it's something. Anyway, that is what research on antimatter tries to answer. What causes the disbalance between matter and antimatter? Essentially, corporate wants us to find the difference between these two pictures. We are sure there are differences, we just don't know what they are, but we're looking for them. For example, you might know of the hydrogen atom, a single proton with an electron whizzing around it. It has an antimatter equivalent, anti-hydrogen, consisting out of an antiproton and a positron. In 2018, research showed that antimatter hydrogen has the same color as normal hydrogen. This was not known before, but it shows that at least this type of physics indeed works the same for antimatter as it does for the normal matter that we know and kinda understand. Looking at the color of something might sound trivial, but remember, making antimatter is hard, and making antiatoms is even harder. And if you finally have made antiatoms, how do you store them long enough to look at the color? Everything we make is made out of normal matter, so you can't touch it with anything. So although we know some things about antimatter, there's also a lot we don't know yet. For example, if electric charge is one of those things that changes sign for antimatter, is mass also one of those things? If that were the case, the mass of antimatter would be negative. So if you would enter it in the formula for the gravitational force, the force would also be negative. Sounds crazy, but just means that the force points in the opposite direction. So, if mass flips sign for antimatter, antimatter would not fall down, but it would fall up. Okay, I'll take that back. That would be just plain weird, but here's the point. We don't know if mass is one of those things that flips sign. We have never measured in which direction antimatter falls. So yes, this is an active research direction. Creating antimatter and letting it fall. So, what is antimatter? The answer, it's like normal matter but with some properties flipped. It is one of those things that nature can create, but also something we have just started to understand. Or rather, started to understand parts of. There are still many open questions and very, very few answers. For now, at least. Camera. Can you turn on the camera? Cool. Ooh, interesting. Yeah, interesting. Yeah. Cats doing science since the invention of tables.